All right, I'll get started. My name is Sungho Park, and I'm working at ByteDance. I've been working here for about 3 years, a bit more over 3 years now. And I'm going to talk about how we are leveraging Velox to accelerate Elasticsearch. And so here, a small disclaimer, like I'm going to focus more on what we do with Velox rather than like what we're doing on the Elasticsearch. We partner with a separate Elasticsearch team that unfortunately is not here today that uses what we have done on Velox to enable their query system on Elasticsearch. So let me just go over like what's going on with Elasticsearch at ByteDance. And the biggest reason that we call this Elasticsearch is that their data here is based on Apache Lucene, which is a kind of a full text service, like they kind of a data source where they hold all of their data for Elasticsearch. A key thing here that I want to point out is that this is using non-SQL, or we started off with non-SQL queries. I think here at PrestoCon, like Presto, we're always dealing with SQL, especially ANSI SQL. But I just want to talk about how we were able to run other queries that are not SQL, which is on Elasticsearch. So the main use case that we have here within ByteDance is mostly for like the ads team trying to let users query data for ads. And these users here have like very high availability requirements. The latency at most times are at a sub-second level. And the rate that we see these queries is like thousands of queries per second. So this, if you kind of do the calculation, this leads to around like 100 million queries per day. And in fact, we'll actually be seeing more and more of this. I think we are still on the rollout process for this, adding Elasticsearch through Velox. We have already started like a gray production rollout right now. But eventually, we are going to expand this to like 500 machines, which have like 1 terabyte of memory and 64 cores, so pretty big machines. And here I have like handling 100 million queries per day, and I think this would be actually the bare minimum. I think eventually we'll probably be seeing billions level of queries per day. So what is the reason why like Elasticsearch started to want to use Velox, something like OLAP in here? The biggest problem of Elasticsearch within ByteDance was that the planner and executor are coupled together. So a lot of the nodes, like worker nodes or machines, are doing all this together. But we don't actually need to do this. And we see this a lot in OLAP services like Presto, where we have a separate planner that can create the plan for us, optimize the plan for us, and then do the execution. And I think overall you've seen a lot about Prestissimo and Velox doing that execution for you, and seeing our Presto's improvement through that. And overall, like we are dealing with users from advertisers, and I think the long delays in those queries can highly affect the user experience and often the stability of the cluster itself. So there are 2 big kind of cases that we cover for Elasticsearch here. Is that one case we're going to highly focus on aggregates with filter. You can add some other stuff like limit or order by, things like that, but the focus is aggregates. And here we're thinking about like very high QPS, but not too much computation. Relatively. And then another case where we're going to focus on more different complex queries, maybe involving multiple tables, like so doing like a join and things like that. One thing to note here, I think, so the aggregates here is something that we want to accelerate on Elasticsearch. For something like joins, a lot of these queries, we're actually not even supporting Elasticsearch. So what the user had to do is query a table or 2 tables separately, and then they would manually do the joins themselves with that data, and then do whatever operation they needed to do. So on that side, we're actually adding new support for ElasticSearch to handle different query behaviors. So we have wider query coverage for them. So I'm going to quickly go over like the kind of API interface that we created on Velox side to open up a bit of like the Java APIs so that Elasticsearch can leverage Velox very easily. So the 4 main steps that I'm going to talk about is first the query plan creation. And second is the data fetch, so how we add data into a Velox task. And then third, executing the task or query itself. And then at the end, getting the result out. There's some miscellaneous APIs that we also added that are not crucial to the main workflow, but are very helpful. So for example, there's getting the metrics or how we decode some of the results. Oftentimes, the results will be in the dictionary encoding or different types of encoding, and the user needs to be able to decode that. And then the third is being able to add a customized configuration so that we can add any feature flags or things like that for any optimization opportunities, maybe on operator like aggregation. So one of the main things here is that Elasticsearch, Apache Lucene, is heavily on Java, like Java only, and similar to, I guess, how Presto was before, and Velox is in C++. So here we have to do a lot. We have to do a lot to bridge that gap and make sure that we can call these APIs from Velox and do all these APIs with the C++ native code from Java side. So for this, we actually use a library called Java CPP, which is an open source JNI wrapper library that helps us kind of wrap the Velox around a Java wrapper. And how we kind of do this is that Java CPP usually requires us to have a lot of bindings. For every single C++ header, you would have to have a binding on the Java side. So for example, I think Velox has a lot of dependencies like folly or things like that, and we would have to write a header or binding one by one on Java side. And we didn't really have the time to do that. So the workaround for that was that we would use a dynamic library from Velox. So we compile Velox as a dynamic library. We input that into Java side, and then we just write some dummy headers so that we don't have to include folly here. It's still used in Velox, it's just not, we just don't have to define it on Java side. And then we use that and wrap all of our Java APIs together as a jar, and then the user can use that jar to access Velox pretty easily. I think the main challenges around here was that Java memory allocation and C++ memory allocation or Velox memory allocation can look very different at times. That is still something that I think we're constantly improving. I think that's where we've seen a lot of issues come. If there's a memory leak on C++, it's not very easily caught on Java side, but may cause a seg fault, things like that. So the first API to talk about is a query plan creation. So like how does Elasticsearch put in the query? Like how do they define the query? So we have a build plan API, just inputting like a string. And here, what we allow is that Elasticsearch internally will use something called a DSL, kind of our internal method of communication of a plan for this query. I'll show you an example in a bit. But once we get this DSL, you can think of this DSL as like a JSON. We'll convert that DSL or JSON into a Velox logical plan so that it's ready in Velox terms to execute. And that also, during that process, it also kind of prepares the data schema so that when we get the inputs, we know what data schema to prepare for. I think when we started, the substrate support was not as great, but now I think it is a bit better. So we did actually add the substrate support event. So this is also allowed, but I think in our current internal use case, we still use the DSLs. But I think in the future, we might want to think about moving to using substrate instead of DSLs. OK, so this is kind of an example query. On the left side, I have a SQL. Initially, within this project, we actually didn't have this SQL at all. What we have is just this middle ground, this middle JSON-looking thing, which we call it DSL. So from this DSL, we input it into the Velox side, and then we turn it into this kind of plan. Yeah, so if you look at this middle one, this one actually only talks about the partial plan. So it kind of maps directly to the top right. The next step here is a data fetch. So how we add inputs into our Velox task, how we prepare it for it to be ready. So here we add two kind of APIs for the Java side to signal Velox. One is add input, and then the second is no more splits. So it just signals that there's no more inputs left. I'll talk about the data format in a bit, in a few slides. There was a lot that we had to do around this to be able to handle the Java versus C++ side. Yeah, so from the ElasticSearch side, for them, they wanted to use arrow arrays instead of like a Velox vector. So what we do here, this API is going to use arrow data. So from the ElasticSearch side, their code looks like they get the data from Apache Lucene, they put it into arrow format in memory, and then pass that into Velox. And then when that's passed in, from Velox side, they need to get Velox formatted data. So we will convert those arrow data inputs into Velox. And here, we try to zero copy as much as possible. If we have to copy, we have to, but that can cost some time. So as we do those the add input or no more splits, we have the task running already. So that's why I'm kind of skipping that task execution step earlier, but you can think of those APIs handling starting that task execution already. And then once that happens and the task is finished, then we need to collect the result from Velox. So we're holding that result in a C++ form, and we call collect result API, and we get that result back. At first, that's a Velox vector, and then we change it into an arrow format so that the ElasticSearch team can easily use the arrow format. Yeah, so I talked about arrow, and I just want to talk about why we are using arrow. I think currently in Velox, the Velox vectors are not well supported for every type of language. I know that Velox is actually working on this. They have a project on PyVelox. I know that I think they're trying to leverage it for ML cases. But for the Java side, there hasn't been too much. I think Gluten might have open sourced a bit of it recently. But yeah, so because of that, we started using arrow first because we didn't know how well we can convert that Velox vector into Java format. But for arrow, there's already a lot of good support across multiple languages using the C ABI. So that helped us be able to move this data across Java and C++. Another plus that we saw on here was that the ElasticSearch was having to serialize a lot of data and move that across different nodes or to the user, things like that. And we've seen that the serialization of arrow memory layout was very fast. So yeah, if you look at this diagram, how the whole workflow goes is that the ElasticSearch team will start from Lucene, put this data into arrow format, change that input that into Velox, and then Velox will convert that into Velox vectors, do some aggregation, whatever process that we want to do. The result will give out an arrow output. And you can think of this data node up here as kind of like a worker, a partial plan, partial aggregation, and then move that data across the network to prepare for the final node. And then the coordinator node, who kind of collects all of the partial results together, will get an arrow, put that into Velox, and then Velox will output an arrow result, and at the very end, the Elasticsearch team can get that final output. Yeah, so just going a bit more deeper into detail of what that just meant right there is that we start off with arrow in Java, which is like an arrow vector. And we have to first convert that into the arrow C data interface, or arrow C ABI. What that looks like is a pair of arrow schema and arrow array. Those two together create one vector. And we use those data structures, and we can pass them as pointers to C++. Java gives some APIs for this so that we can easily get the pointers of this. I think usually Java is not very friendly for getting these pointers like this, and C++ is very friendly for this, but Arrow Java supports this. And then once Velox gets this as pointers, we convert that into Velox vectors and then do the execution. We get a result as a Velox vector, and then we pass those pointers back out onto Java side with the C API. Yeah, and I want to talk about a bit of the different types of executions that we kind of do for Elasticsearch. So there's a single thread mode and a multi-thread mode. And the first single thread mode is what you think you just add all the inputs together and then tell the task to start running and then finish and then collect all the batches in one thread. So you just have one thread doing all of this. The biggest reason for this method, which actually Velox provides very well already, is that Elasticsearch here was actually trying to do queries at a very fast level, so like very high QPS. So they didn't want to overload their threads with thousands of queries per second. So they wanted each thread to be handling one query at a time. So if one thread fails, it will not affect 999 other queries. That was the main use case here. And then we also support the multi-thread, which is kind of a normal use case. We just start, and it's kind of a streaming way. So a lot of times, Elasticsearch will be reading from Lucene one by one, or not one by one, but like batches by batches. And they want to add all those batches into the Velox task, but it may be too big. So they will take, probably like in a for loop, add these inputs. And we wanted to make sure that we can process as much as we can as we go while we're still reading from Lucene. Of course, there are some limitations depending on what the operator is for this, but we do the best we can so that we don't overload the memory with, for example, if we have 100 million rows going in, we can put 10 million at a time, and then maybe the first 50 million will be processed by the time we're adding the latter half 50 million. Yeah. And we've already kind of opened up the possibility to add a query configuration so that can adjust anything. We can add new feature flags for it to make sure that we can optimize the queries. So I mentioned Elasticsearch is doing a lot of aggregations, and if I know what query, a bit more details about what kind of aggregation they do, it's possible that we can just highly optimize that aggregation process specifically for them. And I think often we see them actually do a lot of repeated queries. So that is a very high optimization point. So let me just go over like a quick rundown of like how their aggregation case looks like. So you'll see kind of workers and coordinators here. It's kind of similar to Presto, but but you can think of it as the coordinator as kind of the sync node that gets all of the partial results together and then finalizes the end result. So they will have like, let's say 30 workers do partial aggregation. And the purpose for this, maybe they have like 30 shards of data that they want to all parallelize at once and split it into different worker nodes. So they will do like a partial aggregation on each worker node separately, and then those will all go into the coordinator at the sink and do the final aggregation with these partial results. So this helps them from Elasticsearch to query multiple indexes at the same time. And I think that's kind of highly how Lucene is used often for their Elasticsearch case. I wanted to also just highlight some features that Velox has, or some features that we have added to Velox that helps for Elasticsearch. Apache Lucene is heavily dependent on dictionary encoded vectors, and Velox already has support for that, which has helped us a lot. And I think that helps the performance in a big way to be able to handle these dictionary encoded vectors. There were some other UDF that we implemented into Velox to handle the same use cases that Elasticsearch already is doing. That includes data sketches library, a separate customized date histogram function, and a few Spark functions. Some of these functions, I think, we already see in Presto as well. Some of these are more specific to Elasticsearch itself, like date histogram. Another case that we looked at, so you can kind of see that it's similar to Presto, but the difference is that Elasticsearch is kind of the one that's handling the coordinator workers, scheduling that. And from Velox side, we are only caring about how to execute a query. Like, given a plan, how do we execute that query? So from the Elasticsearch side, if they want to do some different types of queries, like partitioning the results, for example, like a shuffle join, so they need to partition it and then send that data across different nodes, and then do aggregation on each node separately, things like that. Usually, Presto kind of already handles that. Like the coordinator will already handle that for us. But in this case, Elasticsearch is kind of acting as a coordinator, and we wanted to give the ability of any coordinator to do that. So we've also kind of modified a bit of the operators within Velox to be able to handle this case, to return partition results. OK, so here's I guess the cool part, the actual numbers. We can look at, these are pretty big sizes. We have like 50 million input rows or 100 million input rows at 1, 2, 3 dimensions. Dimensions here, I mean this by like a group by. So like how many keys that we're grouping on. So you can see the left table, we have 50 million input rows, and we output 1,000 or 30,000 result rows, showing kind of our cardinality of the group by. And you can see for the 1,000 case, we go from 3.9 seconds to 1.4 seconds. In the 30,000 case with 2 dimensions, we go from 4.9 seconds to 1.6 seconds. The composite here means what Elasticsearch was doing previously, and Velox is after they switched to Velox. And then, even bigger case with 100 million input rows and higher group by or more group by keys, 3 dimensions. You can see the result row count: 10 million, 5 million, 2.5 million. In the 10 million case, it didn't even work for Elasticsearch. But now Velox does it in 9.2 seconds. 5 million case, we went from 80 seconds to 4.5 seconds. 2.5 million rows, we went from 40 seconds to 2.6 seconds. So we actually see like a huge improvement. I'm focusing on the aggregate case here because for the joins, it was hard to do a comparison. As I mentioned before, the Elasticsearch case, what they do is, for joins right now, is that they have to actually manually do the joins separately. They're outside of the Elasticsearch system, like get each table separately and then join them together and then do whatever process they want. So it's hard to compare because that's kind of based on like what the user does. But instead now we are supporting that directly so that they don't have to go through all these manual steps, and instead they can just provide a join, provide a query with a join. Yeah, so some future works that we are thinking about is, I think previously when we talk about like arrow versus Velox vectors, you might have the question of like, well, like, isn't that very costly? It's actually not that costly, but it definitely is a cost, especially when the data is too big and we need to copy all the buffers. So I think we do want to zero copy more and more of this, like support zero copy for whatever we can. I think the big case is like the string vectors. Strings have different buffers, which is harder to zero copy. But also, like, we might not even have to do this if we can actually just go directly into using Velox vectors. If we have Velox vectors, if we have the ability to create Velox vectors in memory through Java instead of C++ or other languages, I think that will also be a very good way to do this. Another case is we also talk about how we go from Lucene to Arrow to Velox. I think we also want to think about maybe we can just connect directly Lucene to Velox. This was kind of not done based on like how complex Lucene is, and from what the Elasticsearch team says to me is that that would just be like basically a recopy of their Java Lucene code into C++. I haven't looked too much into that, to be honest, but I think that would be a good step if it is easy to create that connector. Then we don't have to do all these steps from Arrow to Velox. And then, as we are handling and juggling between Java and CPP, Java has its own memory allocator for Arrow arrays, and Velox has its memory allocator on its own. And so oftentimes, if I'm sending a vector in from Java side, or if I'm sending a vector out from C++ side to Java side, this memory can be kind of swapped around in a way. So we need to be very careful about like freeing the memory, freeing the buffers here, and making sure from Elasticsearch side after they give the data to the user, or they copy the data to their own allocator. They need to make sure that they deallocate from Velox side. So these are like nitpicky details that are pretty annoying to deal with. So I think that is kind of the next step that we can try to solve so that we don't run into any of these memory issues. We've seen a lot of these memory leak issues cause sec fault on Java side, and that is actually a big pain. Like you see the error on Java side, but not on C++ side sometimes, and you just get a sec fault out of nowhere, and you can't really pinpoint it very easily. I think that's one of the biggest challenges that we see, and I think that's one of the things that we want to solve completely. Yeah, so that's it. I just want to mention that our team is hiring. But yeah, I think I have like a few minutes if there are any questions. Yeah? So I think the question is, do we enable any cache for the performance tests, right? No, we do not have any caches there. So it's just kind of straight up. So is the question based on like how a cache works on Velox? I don't think my team has focused on that so far in terms of like a cache for Elasticsearch, but I don't think it should be a blocker. I think you can have a cache kind of have that connector set up for a cache for Velox to run on it. Yeah. So the question is the conversion between arrow vector and Velox vector expensive? So it depends. So for example, like a big int vector, just normal integer vectors, it's not expensive at all. It's just moving around pointers to the buffer. So it's kind of an O1 operation, and it's fine. But sometimes it will be expensive, I think, usually for string vectors. Velox has a completely different string view type. Arrow does not use string view type. So the buffers are very different, and they would have to, basically, if you have like a 1 million count string vector, then you would have to copy the whole string buffer.
So did you consider any other alternatives to Velox which already work in arrow format, like Candy? Oh, sorry. So did you consider any alternatives to Velox? Because in Velox, you have to convert to Velox vector and then do processing, right? So any other open source things which directly do processing on arrow format itself using SIMDs or whatever?
Yeah, I think we did actually consider, I'd say we haven't looked too much, but we are aware of like Gandiva and those different abilities. But I think it was a big test for us to see how good Velox is. I think we kind of started developing this at the same time, like before Prestissimo was fully there. So I think when we look at ElasticSearch, some of the queries, like I said, it's just aggregations. So it's a bit easier to support. So I think that's why we just wanted to focus on like how well can Velox do for this case first, and then go on. But I think we are pretty open to thinking about different types, like different systems instead of Velox as well.
Thanks for the talk. Two questions. First question is, you mentioned use the Java CPP library for the GNI part.
Yeah.
So you mentioned the overhead, like you have to do like Java file to C++, like header file mapping.
Right.
So what are the benefits you pick this library instead of just simply use the GNI?
Yeah, I think you could do it directly through JNI. That is a possibility. I think previously we were in collaboration with another team in our company, and I think when they tried JNI, they had a lot of trouble with the memory management, as I mentioned about like Java allocator and the C++ allocator. They would constantly see memory leaks. So we just kind of swapped to Java CPP, which does a much better job of deallocating resources for us directly. So that was kind of one of the biggest reasons, biggest advantages of Java CPP.
Cool, thanks. So you mentioned the benchmark results. So right now, is this feature in production? And do you have any production stats to share?
Yeah. So we do have it running in kind of gray rollout stage. I think we plan to fully change the whole ElasticSearch with Velox eventually by in next year. And I think to share just some of the stats, I've only been able to see just part of it as well because it's mostly on the ElasticSearch team side, which is a separate team from me. We see at least generally 30% latency decrease when using Velox.
Great, cool, thanks.
Yeah, I think we're probably out of time, so I'll be around. So if there's any other questions, come find me and feel free to ask any questions. Thank you.